Okay. So we'll start today's lecture by playing Flappy Bird. Is there anyone who's not played Flappy Bird? Not played? Okay, so please go back to your rooms and do play Flappy Bird once. It seems like a very simple game. There are a lot of variants of this game. I picked up the one where I could score better. So you'll see the case. So I'll start the game. So this is, it takes a bit of time, 2-3 times you need to play and then you get better. But this is the main crux of the game. If I play it again, you can tap or press space. There are only two things which you can do while you're playing the game. So you can either not do anything, which means you'll go down due to gravity, or if you press the tap or if you press space, then the bird flies above. And what is the goal in this game? Is to score as much as possible. Let's see if I can cross the first hurdle or not. Okay, at least one. Okay, let it fall. So you saw that the score was 3. You saw that the score was increasing by 1 each time I crossed one pair of pipes, right? There is a vertical, there is a pipe coming from the top and one from the bottom. You need to clear those. So I showed you this game which has been, the code is modified from this GitHub repo. The specific code which I picked up didn't have the score functionality, so I took a bit of help from ChatGPT. I didn't know much of Pygame, etc. So this is built on some tools in Python called Pygame, which you can use for very simple gaming environments. Okay, so let me ask this question again. When we are playing this Flappy Bird, what is the goal or objective? Maximum distance or maximum score you want to go ahead. What is your goal when you're playing the game? Sorry? So I just wanted to decouple you versus the bird here. The bird's goal is to maximize the score. What is your goal? Right, no. So, but why are you playing the game? For some recreation purposes. Right? I just want to decouple those. Eventually, the way you feel recreational benefits is by getting some scores, etc. Right? So the goal or objective is to maximize this particular score. Right? Now, in every game that you play, there is some notion of a score. More or less every game that you play. Like Super Mario also, there you have different levels. Right? You need to again score more. And there the scoring is also slightly more complicated here than here. Right? So, Super Mario, do you score more if you have more time left? Right? At the same time, there are more functionalities there. For example, you can collect different kinds of coins. Right? You can also kill different kinds of opponents. So, it's a much more sophisticated gaming environment compared to this one. Okay, what are the different actions which the bird can take? We've already discussed this. There are only 2 actions. One is to not do anything, the other is to try and go up using the space or the tap, right? So we're trying to gradually define a few terms which we will be using in order to understand this lecture for reinforcement learning. Thus far we have looked at the goal of the objective, which is to maximize the score. The second being the actions which we can take. In the current case, it's a very simple game, so only 2 actions. Super Mario, what is the number of actions you can take? 1, you can go forward. Second, you can go back. Then you can jump. Then if you have got the power, like if you have grown, then you also get or you also get the gun. Right? So there are few various different kinds of actions you can take. But in this game, we have got only 2 simple actions. Okay, who is playing this game? I mean, we'll call the player as the agent for today's lecture. It's generally you or some algorithm which will be playing. Where are we playing this game? Of course, like you'd say that I'm playing on this laptop, but where is the agent residing? Is the agent residing in some physical world? No? Where is the agent residing? So if you've seen the Matrix, you should see that as a hint. If you've seen the Matrix trilogy. So where is this agent residing? Sorry? Right. Yeah. So the agent is residing in some coded environment. Right? The code is actually available. Like if you want to see the code, if I this is the entire game where the agent resides, where the agent plays. There are various things like gravity, speed, screen width, height, game speed, ground width, ground height, pipe width, pipe height. And then there are various kinds of physics equations which are being put. Like your speed is increased by gravity, by some notion of gravity. If you bump, then the speed is reduced. If you hit the pipe, something happens. If you hit the ground, something else happens, right? So all the laws of, simple laws of physics, some restricted laws of physics have been added into this game, into this code, which we'll call as the environment. The environment is where the agent is living, is trying to maximize their own reward. So therefore, we can see in this slide that this particular piece of code is the environment where the agent is residing, is living. Okay, what does the environment provide to the agent? Or when you're playing any particular game, how do you decide whether you should be tapping or not tapping, or in the case of Super Mario, you should be collecting a coin, or whether you should be jumping? How do you decide that? Anyone? Based on the changes in the environment. So what you're referring to is that the environment will change based on what you're doing. That is one thing which we need to note. Second, the agent, you said that the environment is changing, but what is the environment giving to you so that you perceive the change? In the case of a game, what do you actually see? Do you see pixels? Different color coded pixels? But are all of those pixels useful? For example, if I am looking at this particular game, is the pixel showing the cloud important to you? No, it is not adding any value. So therefore, the environment is giving you certain things like the rewards. This is actually a bit of a misnomer in this case. Reward and score should not be considered the same thing. The agent is showing you the score, but for every action that you take, the agent gives you something known as a reward. We'll come to what exactly a reward is when we look at some practical examples. But think of it as for every action, the environment will tell you whether you did good or bad. And it will give you positive, negative, some kind of a reward. In this case, each second that you do not fall, the environment should give you a positive reward because you still remained alive in the game. If you fall down or if you hit the pipe, what kind of reward should the environment give you? Negative, because you've fallen down, right? So you're going against the objective, which was to maximize the reward or the score. So the environment will give you the reward on every action that you take. The environment in this particular case is also giving you a bunch of observations, which is just some pixel level information. Now, how do you think we will process the observations into something more useful? As I discussed, some of the pixels are not useful for us. For example, the clouds are not useful to us. A lot of the blue sky is not useful to us. These buildings are not useful to us. The green trees are not that useful to us. What do you think is useful for me to decide whether I should tap or not in this particular game? Someone said distance. Distance to what? Sorry? Okay. Distance to the obstacle. That is one thing which is useful. But in which dimension? In the vertical dimension, in the horizontal dimension? And we have two pipes. Okay, so let's play the game again. There was no pipe at this point of time, but I fell down, like the agent fell down. So what do I need to consider? The vertical distance from the ground, right? It should not go very low. So that's one thing. Second, if I play it again, again, what do I need to consider? The horizontal distance to the top pipe, the horizontal distance, to the top and the bottom pipe is the same. But you also need to know where are you in between the top and the bottom pipe. Where are you in that gap? You want to be somewhere in the middle when you are close to that. So these are a few things which you want to take out from the observations. So what we're saying is that there are a bunch of observations that you're getting, which is some pixel level information, which is very dense, I would say, but we don't need all of that. You want to somehow extract out something more meaningful, something more useful for you, which we will say is defined by the state, which is, you can think of it as some processed kind of information into something which is a summary for where the agent and the environment are interacting, how they are interacting. So, for example, for this particular case, I would pick up, let's say, only three elements: the vertical distance from the ground, the horizontal distance to the pipes, and let's say the gap between the pipes. Something to that effect. If we consider these three, we'll be more or less be able to capture all the dynamics, right? So therefore, we are defining the state as some processed kind of information which can encode the agent in the environment, which can summarize the agent in the environment. Okay. Is the notion of time important while we are playing the game? Yes? No? This would also depend on the connotation in which you process this question. The way I was trying to ask this question is that the state at time t0, is that anyway related to state at time t1? Yes? No? How are the two related? So if I am at time t0, I'm here. If at time t0 I was, let's say, here, and at time t1 I'm pressing the tab button, I will only go up. So what we are saying is that two consecutive states, they are coupled via the previous action that you took and the response which the environment gave you. Right? So this is where this problem becomes slightly different, very different, in fact, from supervised learning. In supervised learning, you don't really have this notion of the update of a state. There you are given a prediction problem, you just predict your response variable with respect to the input variables and you're done. But here we have a sequential nature of a problem. Right? Our goal is overall increase the score, but the different states are connected to each other by the actions you take and the response which the environment gives you. So therefore, for reinforcement learning, we end up with something like this as the block diagram. We have an agent and we have the environment. The agent takes certain actions at time t. We'll call them A of t. In the case of Flappy Bird, it's just two actions: tap or don't tap. If you give the action to the environment, what does the environment now give you back? If I press tap, if I don't press tap, what is the different things that I'm getting? Let me go back to the game again. So let me just keep on pressing tap and you tell me what is the new thing which the environment gives me. Okay, what happened when I took certain action? What did the environment give me? It gives you certain kinds of rewards. Second, it also changes the graphics overall. Right? So the environment is also changing, which means the observations are changing, which also means that the state is changing. Right? So we saw that if I kept pressing the tap button, the bird went out of the screen, out of the visible area. So it means the observations have changed, the state has changed. And because I said that every second that I'm alive in the game, my score should be increased. because that's a pseudo way of understanding my overall score if I can stay alive. So therefore, the agent takes certain actions, tap, not tap. The environment will be considering the current state in which the agent was and the action that they have taken. So let's understand that also once. I will do the same action, but starting at different points, different states. So firstly, notice that I will keep pressing tap right from the word go. This was one behavior. In the second case, I'll do the same action, but I will start from a different state. Initially, I will not press tap. Or I was a little late, but assume that I pressed tap. So, can you notice that depending on the state that you are in, even if you perform the same action, you will likely get a different response from the environment, right? So, therefore, the response from the environment is depending on what two things? The state in which the agent is at time t and the action which the agent has taken starting from state st and at time t. And then what the environment gives you is a reward at time t which is called r of t, and it gives you a new set of observations which you can then process to get the state. Right? We've been talking about state as some compressed version or some summarized version of the observation. Sometimes these two words are used interchangeably, but I will just separate them out today. Right, so this is the main block diagram. The agent is in some particular state st, they take some action a of t, they send that action, the environment processes it, gives some reward, whether your score should be increased by 1, decreased by 1, whether you are still alive, not alive, and it will give you a new set of observations from which you get some new state, and this loop continues. Does this loop continue till infinity or no? Till you reach a particular state, right? Or the game ends, the game terminates. So till the termination state. In our case, the game ends whenever I either hit a pipe or I hit the ground, right? So this is not as such an infinite loop. You should think of it as an infinite loop, but there is a break condition. Okay, so enough theory. Now we'll go and look at some environments in something known as OpenAI Gym. Has anyone used OpenAI Gym before? Okay, a very small subset of students have. So think of this as a library where certain environments are predefined for you. Right? Flappy Bird was some specific environment. So this is the Flappy Bird environment where all the physics is given to you. What happens when a particular thing is done? The response from the environment is given back to you. The reward that you get is also encoded. All of that is done here. So OpenAI Gym contains many such environments. So if I look at the environments present in OpenAI Gym, there are quite a few of these: cart pole version 0, cart pole version, mountain car, continuous, pendulum, acrobat, etc. For now, the first case, we'll be looking at an environment called mountain car. Render mode equal to human so it shows you the display so that you can actually play the game. You can think of, you'll get the visual response also. So this is the environment. What do you think is your goal? You have a car on a mountain and you have a flag here. What do you think is your goal? You want the goal, what you're saying is the policy or how you'll do that. The goal is to just reach the green flag, whatever, yellow flag, reach at the top. Right? But this seems like a very simple problem. Why should I not just keep going towards the right and I'll reach the goal? Or is there any problem in that? If I keep going right, should I be reaching the goal? That's how you typically think if you're driving a car, right? You're moving in the direction of your goal. But why doesn't that work? What is the challenge?
The here is the physics has been defined as arranged in such a way that the incline will provide it opposite acceleration in upward direction.
Okay, so we will come to that in a second. I just wanted you to whet your appetite. So you get some observation from the environment, the observation of the state. In this case, I am using them interchangeably. You get a two length vector as your observation. What do you think this observation could mean? You have to somehow define the mountain car you're defining them via two coordinates. What do you think they could mean? Speed in the x and speed in y. What about the position? Do you need to know the position? So let's go to the documentation and see what they tell. They tell that it's a part of a classic control environment. The action space is discrete, observation space is 2. The observation high is 0.6.07 and low is minus 1.2, minus 0.07. They have two elements. One is the position of the car along the x-axis. It goes from minus infinity to infinity. So you can have minus 2 to 2.4, something like that. So the actual variations are minus 1.2 to 0.6. This position, here you can see my mouse, is probably minus 1.2 and this is 0.6. Okay, it's getting stuck for some reason. Minus 1.2 to 0.6, and the second one is velocity of the car. Again, the velocity can be negative as well as positive. Negative means going in this direction, positive means going in the right direction. So therefore, they are using this two length tuple or vector to define your observation, or you're defining your state. Next, they have something known as the action space, which says it's a discrete of 3. It means there are 3 states, there are 3 different actions. So it's a discrete action space. If you look at the number of actions, they are 3. What do you think these 3 actions could be? Yeah, the action space is discrete of 3, which means you can, 0 means accelerate left, 1 means don't accelerate, stay as you are, and 2 means accelerate to the right. So they have simplified the problem, they are giving you just 3 possible actions. So therefore, this is known as a discrete action space. Could you think of continuous action spaces also for such problems? When you are driving your car, do you only have 3 actions? Or let's say if you're going ahead, do you have only 3 actions? Accelerate forward, don't accelerate, or reverse, or do you have something more? Do you also have the degree to which you accelerate? Right? And that is on a continuous scale. So therefore, we are looking at a very simple discretized version of this problem where the action space is discrete, but in a more typical, more practical setting, the action space would be continuous. But that introduces more complexities which we'll not get into today. For today's class, let's assume the action space is discrete. And they've also given the physics, which is the transition dynamics, which we assume we don't have access to. The reward is -1 for each timestamp. So what does this mean? You want to reach your goal as quick as possible. Every second that you waste you're getting a negative reward. They start the car and the position is between -0.6 and -0.4, and the starting velocity is always 0. The episode ends if the position of the car is equal to 0.5, which means you've reached the goal. Second, the length of the episode is 200. So each episode means each time you do a trial, Each time you play the game, you can't go beyond 200. So the maximum negative reward that you can get is minus 200. At that point, they just want to stop the game so that you don't get stuck in infinite loops. So therefore, it's also now important to see, we said that the action spaces could be 0, 1, 2. They give this nice feature to randomly sample from the action space. So for every time, let's say I randomly sampled from the action space, I get, for the 0 time, I get an action 1. For the next time, I get 0, 0, 0, 2, so on and so forth. Okay. Okay, so I was saying that our environment has given you an action space, but it is also giving you an option to randomly sample from that action space. Why do you think that is useful? Why might it be useful to have this ability to randomly sample from an action space? No. So the action space sampling means, so the starting point they are fixed. Let's say that the environment gives you a starting point. You're choosing an action at random. Action at random means that wherever you are, you could either go left, right, or stay there. Why is that ability useful to have such an option in the environment? What was your goal? To reach the flag. The ability, if you have the random samples, a random action, the question that I'm asking you, is it possible that with a random action you can reach the top? Is it possible or not? Theoretically, yes. Practically, it will not be possible, and we'll see. That is why it's a good ability to have. So let's say if a random action takes you to your goal in 200 steps. So, and if your very well optimized reinforcement learning deep something policy takes you in 190 steps, you're not doing very well. Therefore, it's always good to have a sense of whether if the random action is able to take you to your goal or not. Your observation space, we have already seen, is minus 1.2 to 0.6 for the position, and for the velocity is minus 0.07 to plus 0.07. Okay, now so this is the main loop in reinforcement learning. This is probably the most important thing for today's lecture. For I in range 100, so for 100 timestamps I'm running this, I'm rendering the environment, I'm randomly sampling an action, I start with some initial observation, I step and I provide the action. So starting with state ST, I provide an action A of T. In this case, I'm randomly sampling that action from 0, 1, 2, and I get a new observation, I get some reward, I get whether it's terminated or truncated or some information, and I then just keep repeating it. So if I run this, can you see that it's sometimes going left, sometimes staying there, sometimes going to the right? But 200 timestamps have elapsed. You can notice how the exposition is varying. It starts from minus 0.044, it increases, it goes maximum till sorry, this is the one. It starts from minus 0.44, it goes till minus 0.63. So we've actually overall gone left, which is counterproductive. But now let's take the next action, which is always go right. How many think that will work? Okay, good. At least 2-3 people think it might work. So now if I have to modify the code, you notice that I have just replaced the action with randomly sampled action to action equal to 2, which means you are always going right now. Right? Everything else is the same in the code, and let's see if this works or not. The agent is trying to go right, but it goes up and it again comes back because it doesn't seem to have enough momentum. So therefore this policy doesn't work. Therefore it seems that you want to be able to first go a little to the left, gain some speed, some momentum, and then come towards the right. So what might you do in this loop? How might you want to modify this loop so that you can reach the goal? Initially you want to go to the left. After that you want to go to the right. How would you encode that in this loop? Yeah, louder. I know many of you are answering it, but can you be a little louder? First 50 iterations, timestamps, you go to the left. After that, you go to the right. Something like that. So I've encoded that. I said action equal to 0 if I less than k, else 2. And I've defined k equal to 50 and n equal to 250. So for 250 timestamps, I'm running this simulation. For the first 50 timestamps, I go towards the left, gain enough momentum, and then I just keep going to the right. So let's try and run this and see if it works or not. We have been able to reach the goal in 113 timestamps now, right? But this was very hard-coded kind of a policy where we understood the dynamics of the entire engine and then we hard-coded it. But many cases we will be exposed to different environments where we'll never know what exactly the physics underlying is. So therefore, we have to be able to learn this. Basically, we want to be able to see what action should I be taking at a current state. Any questions till now? I've also installed another environment called Flappy Bird Gymnasium, similar to the Flappy Bird. Here the observations which I get is some 12 length vector, where these are the different kinds of variables which my model is having in the state. Last pipe, edge position, last, top pipe, V position, player V position, pair V velocity, player rotation, etc. Right? So these are some important terms which you can use to play the game. I will skip this specific one. I leave it up to you to play this game and understand what needs to be done. Let's revise the block diagram again. We said that we have an agent who takes an action A at time t. That goes into the environment gives you a response in the form of new observations, in the form of a process new state, and a reward at time t, rt. So our goal now, the next couple of slides are a little mathematical. Our goal is to maximize the total discounted reward. I'm not going to all of the details for the maths, why we have chosen all these things, because we just want to do a single lecture in reinforcement learning. So a bit about the course philosophy if you're not understood it at this point of time. The course is supposed to be an introduction to machine learning, where the advanced topics we'll defer to the advanced set of courses. For example, deep learning we have taken about 3-4 set of lectures, but for more detailed you'll have to probably take a deep learning course or a computer vision course or an NLP course. We studied very simple, we'll study very simple Bayesian networks such as naive Bayes model. In more sophisticated, in more advanced courses, let's say in NLP, you might study topics like hidden Markov model. We'll consider a little bit on the optimization aspects. We'll also look at some SVM-like models. But in some optimization methods for ML course, you will study much more advanced concepts of those. So therefore, for RL, we'll also consider just a single lecture, a lecture and a half. We'll not go into all of the details, but we'll just try and understand the intuition behind this. In a course like multi-agent systems, you'll go and understand these in much more depth. So total reward or return R of t, which means you're starting at some timestamp t, is the summation of the rewards which you get from time t till time infinity, till the time the simulation ends, the game is truncated, ended. So we can write this as Ri equal to RT plus 1 plus so on and so forth. Typically in practice, we don't weigh the rewards equally. What we say is that the immediate rewards are much more useful to you in contrast to the rewards which you get much more into this future. So as I'm mentioning this, you can also refer to a couple of very nice lecture series in reinforcement learning. So this one by David Silver is a very detailed discussion about reinforcement learning, goes from the very basics to very advanced. And this is a very nice, this particular set of lectures is a very nice lecture from MIT Deep Learning course, which also covers RL in just one lecture, but focuses much more on the deep learning aspects of RL. So coming back, what we're saying is that we don't want to be giving the equal weightage to rewards. We want to giving more weightage to rewards present as compared to rewards which may be getting few timestamps ahead. So therefore, we have something known as a discounted return, where the rewards going into the future are multiplied by some gamma raised to power the amount of timestamps you are into the future. Gamma is typically between 0 to 1. So therefore, immediate rewards, closer you are in timestamp, the current timestamp, you get the reward is taken more into consideration, in contrast to rewards much more into the future. Sorry, this is getting stuck. Kush, can you call the classroom support again? So we've taken into consideration the total discounted reward, where we're factoring future rewards by gamma power. What we eventually want is to choose a state, given a state, choose an action which will maximize the total discounted reward. That's what you eventually want to be able to do.
So he kind of even said that you need to put up a strong will.
So it's possible that the AC system might not work. So sorry, you'll have to bear with that. So we said that a total reward is what we want to maximize starting from a current state, S of t. You want to be able to choose actions accordingly. So we end up defining something known as a Q function, which is given a state st and an action a of t, it is the expected total future reward which the agent will get by taking that particular action. So therefore, given any state st, you want to be choosing that action amongst a possible set of actions which will maximize your total discounted reward. Right? This becomes easier to understand by something known as a Q table. Let's say that we have a few states in which our agent could be. So I've written state S1, S2 till Sn, and the actions I've defined to be 3. Let's say it's go left, do nothing, and go right. So I've defined this table which contains these different values. Now let's say that we are in state S2. What action do you think we should be taking based on this table? Our goal is to maximize the expected reward, discounted reward, which we are saying is being captured by the Q table. The Q table is having this pairwise storing of state, comma action. For the action S2, for the state S2, what action will maximize Q of S2, comma A? Action 2. So action 2 will give us the highest return, and we should be choosing that. But here I've enumerated the states. I've written them in as if they were some discrete states. But for the problem, for the mountain car problem that we've been looking at, is the state a discrete state or is it a continuous state? For mountain car problem, what is the state that we were getting? The action space is discrete, right? We have 3 actions. The observation space for the position is between minus 1.2 and 0.6, and for the velocity is between minus 0.07 to plus 0.07. Is it discrete or is it continuous? The observation is continuous. Your observation of position can be a continuous value, and so will your be observation regarding the velocity, right? So therefore you can't really put the continuous values here, right? Because then you'll have an infinite length vector, Q table. What do you then do? Here I have shown you a discretized version where the states are discrete, a finite set of states. But in your mountain car problem, these states are not discrete. They are continuous. What do you then do? Okay, how, when we give you your marks, can we assume that to be a continuous variable or a discrete variable? Your marks. Assuming that I have infinite precision, are your marks continuous or discrete? Can I give you 91.124764 and 92.0407345 or 3.14159? Can I give you these marks? Right? So therefore, are your marks on a discrete scale or are they on the continuous scale? Continuous scale. But what? How do you get the grades? Do you get them on a discrete scale or do you get them on a continuous scale? Discrete scale. How do you think I convert the marks from a continuous scale to a discrete scale? By quantization. I break down your marks into certain bins, and according to certain ranges, I give certain marks, right? So now can you think of this solution which I've given you and think of what needs to be done to be starting from the mountain car problem where the observations are continuous, but the Q tables that you want to create, they only accept discrete states. What do you need to do? You need to discretize the continuous space, right? So space which goes from minus 1.2 to 0.6, let's say you divide it into some uniform chunks. Minus infinity to minus 1.2, minus 1.2 to minus 1.1, minus 1.1 to minus 1, so on and so forth. Similarly, we do it for the velocity also. So therefore, you may get something like minus 5 to minus 0.4. So it's a vector position velocity. If the position is between minus 5 and minus 4, and the velocity is between minus 2 and minus 1, that is your state S1. If the position is between minus 5 and minus 4 and the velocity is between minus 1 and 0, that becomes your state 1 and so on, state 2 and so on and so forth. So therefore, we have taken a continuous state and we have converted into a discretized version of the problem. I will now go over this and show you how this discretization happens. This is again just some sanity checks to ensure that the environment is loading correctly. This is showing some random actions. I am dividing now my space for the position and the velocity vector into 3 chunks. Minus 1.2, minus 0.3 and 0.6. And similarly minus 0.07, 0, 0.07. It's just linearly spacing out. And now I'm creating a Q table which is of the form of, let me first show you. Does this seem like a correct thing to do? If the position is between minus 1.2 and minus 0.3, correspondingly if the velocity is between minus 0.07 and 0.0, or between 0 and 0.7, these are different states. So this is, the first row is S1, the second row is S2, S3, and so we have now got 4 states, 3 actions. Does this seem correct? Or is it missing out something? I'll add a bit more to this and create a Q table which looks like this now. Between minus infinity to minus 1.2 for my position and similarly for my velocity. So therefore, starting, I have now defined 16 states. Right, so this is a typical setup. 16 states, correspondingly I have the 3 different actions. So the position comma velocity is my index, is how I look up into the table, state, and correspondingly I have the 3 actions. You can look at the code in detail to understand how I've done this pandas, multi-indexing, etc. And finally, you want to be able to pick up. So for example, our position vector was going between minus 1.2 and 0.6. That was the range. If I give a value of minus 1.3, what state do you expect to get? So just consider this one. Should you be in minus infinity and minus 1.2? So therefore, corresponding to only the position vector, you should be getting a 0, the leftmost bin. If the value is minus 1.2, you get the first bin, minus 1.1, you get the first bin, 0.6, you get the second bin, 5.0, get the third bin. So therefore, I am using this function, digitize function, where I have to give in the bins and I am giving the values which I want to bin. I will then create a Q table. I will show you a Q table created in Pandas, but now I'll show you how typically we'll do it in practice using multi-dimensional arrays, either in Torch-like frameworks or in NumPy-like frameworks. I create a Q table in NumPy, which is number of bins of position times number of bins for the velocity times number of actions, and I'm just reshaping it. So I purposefully kept these values for this 3 cross 3 cross 3 3 cross 3 cross 3 dimensional tensor, so that I can show you if I run this. So if the position is minus 1.3 and the velocity is minus 0.08, then the index for position is 0, the index for velocity is 0, and this corresponds to 0.12. Okay, now you tell me the value, I will not show you the answer. Okay, what should be the value of the Q table? The position varies from minus 1.2 to 0.6, the velocity varies from minus 0.07 to plus 0.07. And here I am giving the position to be greater than the maximum which you typically see, and the velocity to be also greater than what you typically see. What do you expect to see here? If I give it something within the range, you'll see position 2, velocity index 2, right? So basically I was showing how to create this lookup table using this function of np.digitize. So eventually what you want to do in this Q learning framework is that I am first showing you how an untrained Q table, if you use, what will happen. I get an observation from the environment, I render the environment, My observation is a two length tuple, position comma velocity. I discretize both of them to get a position index and a velocity index. I look at my Q table's value for position comma velocity. If I index using position and velocity, I get a 3 length vector corresponding to the different actions. Right? Whenever I index by my position and velocity, let's say it is this particular row, then I get a 3 length vector corresponding to the 3 different actions which I have, and I pick up the particular action. I pick up the particular action which maximizes, which is the maximum, which has the maximum Q value. So therefore, and I choose that particular action, and I now use the same loop as before. You choose that action, put it into the environment starting from the state, you get a new state. Now let's see if this untrained Q table works or not. The untrained Q table, not network, is not working. It seems to be always going to the right. Why is that? Because of the naive version of the Q table I had created. For every state, the action which maximizes, which is giving the maximum Q value, is the last one, if you notice. Corresponding to action 0, corresponding to action 1, corresponding to action 2. So given that the last column is always the highest, therefore it gets up picked all the times. Now we come on to the most sophisticated part of today's lecture, is how do we train this Q learning table. We want to be able to somehow learn these different values. We have already looked at the Q function, which we are saying is capturing the expected total future reward by taking a particular action. We have a very interesting equation called the Bellman equation, which you can see very nicely, very intuitively. You can see it follows from the previous setup that we have written. We say that Q of S comma A is the Q value of taking a particular action starting in a state S, and R of S comma A is the immediate reward you get by taking an action in state S. Gamma is the discount factor, and once you are in state S, you have taken an action A, you go into the state S dash. Once you're in state S dash, and then you can maximize your Q value. The first time it's giving such a hard time. Previous 2 lectures we were also unlucky with the HDMI, so I thought I'll just use AirPlay today. Okay, so I was showing the Bellman equation, which I mentioned is capturing the recursive relation between Q at current state and Q at the next state S dash. You start with state S, you take an action A, you get a reward R of S comma A, you have a discounting factor gamma, you go to the next state S dash. In X dash you're faced with the same problem. You need to choose an action A dash which maximizes the expected future rewards. So therefore we can write this recursive equation like Q of S comma A equal to R of S comma A plus gamma times you're choosing the Q of S dash comma A which is maximized with a new action A dash. So this is the Bellman equation. We use this equation to update the Q values in the Q table, where the update rule might seem very similar to what you saw in the perceptron update equation or similar to gradient descent update equation. The new value of Q of S comma A is given as the old value of Q of S comma A plus the learning rate alpha times the target minus the prediction. Your target is R of S comma A plus gamma times max of Q S dash comma A dash minus your prediction, which is Q of S comma A. Right? So you're predicting that if I'm in a state S and I take an action A, I should be getting an expected reward Q of S comma A, whereas the target what you get via the update rule is R of S comma A plus gamma times max of Q of S dash comma A dash. Right? For a trained network, you'd expect these values to be fairly similar. For an untrained network, you would expect them to be different. But this is very similar to the perceptron update, similar to gradient descent update rule. If we keep applying this update rule for multiple iterations, we'd expect to be able to learn Q values, Q table, which when then used for purposes of playing the game, you'd expect to get much better rewards. So with this equation, I will be using certain hyperparameters, alpha learning rate 0.2, gamma 0.99. I am choosing something known as an exploration setting. I am choosing something known as an epsilon of 0.4. Number of episodes is 2000. Each episode I can actually just keep 200 steps. Why have I changed from 300 to 200 steps? This will tell how awake you were when I was showing the documentation for this environment. If we go back to the documentation for this environment, the episode ends if the length of the episode is 200. So therefore, there's no point writing 300, it will anyway end before that. I am not discretizing my space, my position and velocity space into 20 chunks. All of this code is fairly simple, what I showed earlier, but I don't think we need to go into all these details. This is the main loop. Importantly, firstly, I'm render mode equal to none. I'm setting it to none so that I don't play the game while I'm training, so that it doesn't slow the process. For each episode, I am changing the epsilon. I'll come back to epsilon. I start with I reset the environment. So start with a new observation each episode. Right? Each episode, think of this as each time you're newly playing the game. Your previous game has ended, you've either won or you have lost, but each time you play a new episode, you start from some new state, random state. For each step, you get the observation, you discretize the observation, and you choose the action which maximizes the Q value corresponding to that position comma velocity. Sorry, I'll show the training also. My next observation is S dash, right? My current observation is S. My new observation is S dash. I call it next observation. This action which I am taking is A at T, and this is my reward RT. Gamma factor I already have. So my update equation, Q table of S comma A, my S is position index comma velocity index, is equal to Q table value at S comma A plus alpha times reward RT plus gamma times the maximum value that you get from the Q table for the next position over all the possible states minus the Q table's value for the current position and current state and action. This is exactly this equation. Q of S comma A is Q of S comma A. So Q of S comma A equal to Q of S comma A plus, so this plus equal to just gives you that, plus alpha times R plus gamma times max of Q S dash A dash plus R plus gamma times max of Q of S dash over all the actions A dash minus Q of S comma A minus Q of S comma A. So this is the update equation which I have written. I will first just show this running. So initial few episodes, you see that we had to complete all these steps. We were not able to reach the goal in any of them. After a few episodes, you see that initially it took me 197 steps to reach the goal. As I'm going over more time, you can see that I'm reaching the goal in 160 steps, 140 steps, so on and so forth, in lesser number of steps. Right? First, let me show you now the rewards which I'm getting. So I start with minus 200, which means that I am not able to complete the game. Over time, you can see that for some episodes, I'm getting some good reward. If I use a smoother version of this, you can see that the rewards are improving over time. Now I'll play this game using the Q table which I've learned. Right? So I get my observation from the environment. I get my position and velocity. I take the action which maximizes the Q table's value for that current state. And then I feed that action into the environment. I get a new observation and I get a reward. Let's see this in action. So roughly 156 timestamps you're able to reach the goal. We could have done better if we modify the hyperparameters a little bit. We'll see that we'll be able to do a little bit better. But there'll be a few things which we need to change, which we need to also consider. For example, now, if the number of bins which I'm using, so I'm converting the continuous space to discrete space. If I reduce the number of bins very significantly, what do you expect to get? What do you expect now? Will you be able to learn good Q table or no? You have oversimplified the problem now. Let's see. So overall, you can see it seems that you are getting worse performance compared to the previous one. You have simplified the problem a lot. You're now taking huge chunks of marks. So think of this as in a course, if some student gets 70 and some students get 90, you're giving them the same grade. Right? That is the effect of having a lot of variation for one discrete value. The rewards which you see will be very poor. In between, you got some rewards, and I'll come to the reason why we got something, but overall it's very poor. If we were to play this game, and you can observe it's not a very well trained agent. If we were to increase the bins, what do you now expect to see? Do you see that it takes longer to reach to a state where you start seeing some terminations? But after that, it's reasonably good. If we were to train this particular agent for a lot more number of episodes, perhaps it will do even better. Like you can see that overall it seems to be doing somewhat better. Not hugely better, but seems to be now currently showing a lot of fluctuations. Perhaps if it's trained for longer number of episodes, it will do better. If you again play, right, so roughly 150 iterations it's about to reach the goal. Now there was one thing which I mentioned earlier, which was this factor known as epsilon, which is also known as the exploration rate. So typically when we look at this particular line, line 21, we call this phenomenon as the exploitation. You have already decided some values in the Q table. You're not exploring much. You're saying that just choose the action which maximizes the reward, right? You're not moving out a little bit to the left or the right. You have just hard-coded your thought pattern as to just choose that particular action which will maximize the reward. Whereas what you typically want is some notion of explore, exploit consideration. So sometimes you want to still be able to explore a little bit. Right? Similar to like sometimes you can do a bit of random restarts in stochastic gradient descent so that you don't get stuck in some local optima. right? So what we said is that if numpy.random.rand returns a uniform number from the uniform distribution between 0 and 1, if that is less than epsilon, then you choose a random action. Otherwise, you choose the action as per the Q table. So this is also useful because initially your network, your model is not trained at all. The Q table is completely bogus. So you initially want to explore a little bit. Eventually, after a point when your Q table has been updated sufficiently, then you want to be emphasizing more on the Q table's values. So the typical way in which we do this is we choose an epsilon. I've chosen epsilon to be 0.4, and over time I am reducing epsilon. I'm making for each iteration I'm reducing epsilon. Why do you think that is useful? Why is it useful to reduce epsilon over time? Right. Initially, we want to explore because our Q table is not learned. After a while, the Q table has been learned. You have explored enough. You have gone to different states. Therefore, it makes then sense to be also looking at mainly only the Q table after a while. Right? So therefore, you can now also play with all of these factors. If we had chosen epsilon to be very high, you'd expect initially maybe we train it for more number of episodes. Initially, all the actions are random. So therefore, it might take you a bit of a lucky break to get something. Otherwise, it will take you more time into getting into some reasonable rewards. But after the Q value, after the epsilon becomes small and the Q table has been sufficiently learned, you'll see that we may start getting consistently better rewards. So we now look at the rewards and we plot a smoothened version of them. It's again showing a bit of jagged behavior because I think we still not trained it enough. There is still a lot of randomness to this. But overall, we still expect to be able to reach the goal state quite soon. So while playing around with the different hyperparameters, the best I was able to do was about 130-ish timestamps. I don't know what's the best we can do. That's about the best we could do. Okay, questions on this? There are a couple of other things which we can perhaps discuss in the next class. We'll see whether we have the time or whether you're interested or not. It is using deep learning for Q learning, so deep Q networks. They are much more sophisticated, much more complicated, which means that they also offer more power, but they're also harder to train. Like this is a very simple way to learn the network, to learn Q tables. Okay, in case there is nothing else, we'll meet on Wednesday. The